Hello, this is Ms. Nichols, and this video is on multi-resistor circuits, so circuits with more than one resistor, and a handy little tool called a VIRP table. The essential question today is how can I organize my data and use equations to predict the behavior of complicated circuits. So I find a lot of times kids have a circuit on a test and they're like, what is going to even happen? Which bulbs are going to be brightest? What's going to be on? What's going to be off? How do I know what to expect? And the answer is, it's going to be a combination of things. You're going to use common sense, you're going to use some logic solving skills, and we're going to create a tool called a VIRP table that lets us both calculate numbers and also visualize what's happening at each resistor in a circuit. So as we move into solving complicated circuits, please remember these two rules. Circuits are closed systems, which means our conservation principles are going to hold. Right? Electrons are only going to move through wires that provide a route to get back to the battery, and we're not allowed to lose any electrons, we're not allowed to create any electrons, we're not allowed to destroy any electrons in that process because of conservation of mass, because it's a closed system. And what that tells me is that the same amount of current is going to go out of the battery as is going to be coming back in again to conserve mass. The second main principle is that the total energy used every second in the resistors is exactly equal to the total energy produced by the battery every second. This is conservation of energy in a closed system. So if we have a closed system containing the battery and all the resistors and all the other stuff, we have to be basically transforming all of the energy that's provided into something. And what that means functionally is as electrons go through the circuit, they gain energy at the batteries, and they use up all of that energy before they return to the batteries with no energy, which is voltage left. Let's start by solving a single resistor circuit. So we've got a battery and a bulb together in a circuit. First thing you're going to do is draw the circuit diagram and put whatever information you know. So let's say we know this is a 9-volt battery and a 100-ohm resistor because we measured it. Then we're going to create something called a VIRP table. And of course, VIRP stands for voltage, current, resistance, and power. And we're going to put those names on one side of the column, and then we're going to add a column for each resistor in the circuit. In this case, we have one bulb, we might call it R1, and so I'm going to make a column for that. When we get to more complicated VIRP tables, we're also going to add one additional column for the entire total circuit, but in this case, since the whole circuit is just made up of one bulb, I'm going to skip that step. The next step is to write down the information that we know from our diagram directly in the table. So we know that the voltage used at the resistor is 9 volts, and we know that because of conservation of energy. If 9 volts of energy is coming out of that battery and there's only one place for it to use it, it's got to use it all up in that resistor. We also know the resistance is 100 ohms from measuring it, so that's a good place to start. The goal of a VIRP table is to figure out 2 values in any column, because once you know 2 values, you can calculate the other 2 using Ohm's law and the power equation. So for example, now that I have V and R, if I want I can use Ohm's law to calculate I equals V over R. So I is 9 volts divided by 100 ohms. So 9 over 100 gives you 0.09 amps. So that can go right into your table. Then we're going to use the power equation, P equals I times V, to calculate power. So my current is 900ths of an amp times 9 volts, and I get a power of 81/100ths of a watt, or 0.81 watts. So there you go. You knew 2 things, you solved the other 2, and now we can tell you lots about this bulb. I can tell you how much current is flowing through the bulb, how much current is coming out of the battery, because they have to be the same. And I can tell you how much power is being dissipated. In other words, how bright this bulb is. This bulb is turning 0.81 joules of energy into light every second, and that's a pretty useful piece of information. So what about a more complicated circuit that has multiple resistors in it, not just one? Well, it turns out there's 2 different ways to attach multiple resistors in a circuit. The first is called a series circuit. Series works the same way a series of books does or a series of movies works, where you have one after another. And so the electrons leave the battery, then they have to go through one resistor, and then they have to go through the other resistor before they get back to the battery. On the left is a series circuit with 2 light bulbs in it, and on the right is a circuit diagram for a series circuit with 4 resistors of some kind in it. So you can put as many devices in series as you want. Couple quick rules of thumb for series circuits. Because the electrons have to go through all of those resistors, because there's only a single path, this means that the current is going to be the same out of the battery through each resistor. All of the currents have to be the same because we're not allowed to gain or lose any electrons in the circuit. The voltage, on the other hand, may not be the same in every resistor. The electrons have to use up all their energy before they get back to the battery, so they're going to have to use some energy in each resistor. They don't necessarily split it evenly, right? We're going to actually be using more energy on the bigger resistor, the more challenging resistor, but you can say that the energy provided by the battery is all going to get used up at some point, even if it's different amounts at each resistor. So the other way you could hook up 2 or more resistors in a circuit is called parallel. And if you look at that, the difference is that in parallel circuits, the electrons leave the battery and they actually have a choice. They either go through one resistor or they go through the other resistor, but not both. So on the left, there's a parallel circuit with 2 light bulbs. On the right, there's a parallel circuit with 3 resistors. So in that case, the electrons have a choice of 3 different paths that they can take, and realize that each electron is only going through one resistor as it circles through this circuit, right? It's either the top one or the middle one or the bottom one, but not all 3. So that's really different than in series circuits. And the rules are going to be different as well. In a parallel circuit, the current is going to divide, right? So maybe 1 electron takes the top path and 5 take the middle path and 3 take the bottom path. That's totally fine. It does tell you how much total current is coming, right? If I got 1 in the top and 5 in the middle and 3 in the bottom, then 9 amps of current must have left that battery so that they could split and then come back together again, and those same 9 amps are going to come back. But it's the current that is different because there are multiple pathways to go through. However, the voltage is actually simpler because since each electron is actually only going through one resistor before returning to the battery, those electrons will dump all of their voltage at that resistor because they have to use it all before they return. So the voltage in parallel is going to be the same as the battery's voltage because the electrons only have one place to use all that energy. Okay, so let's take a look at what making a VIRP table for a series circuit would look like. Specifically, this is a series circuit with a 2 ohm and a 1 ohm resistor in series with a 12-volt battery. So we're going to start by making our VIRP table, and as I mentioned before, we're going to have a column for each resistor, so R1 and R2, and I'm going to put a third column on this time for the total circuit. This represents what's happening in the big circuit as a whole, or you can think of it as what happens at the battery, but that column is going to be important. And then we're going to start by filling in the things we know. So we know that R1 is 1 ohm and R2 is 2 ohms, and we know that the total voltage in this circuit is 12 volts. So that's the voltage provided by the battery. We don't have 2 known variables in any column, so we need to do a little bit of conceptual work, some digging, to figure out what another piece of information we could figure out would be. So if you think about this as in our circuit as a school day analogy, right? This is a rough school day, right? We have to go through 2 tests. The electrons have to go through 2 resistors. That's hard. That increases the overall resistance of the circuit. And logically, if you have to take a level 1 test and a level 2 test back to back, hopefully it makes sense to you that the total resistance or the total difficulty of this entire school day logically should be 3 ohms of resistance. It's a pretty straightforward rule. When you have resistors in series, you can add up the resistance of the individual resistors to get the total resistance of that circuit. Good news, we now have 2 known values in one column. So we have 12 volts and 3 ohms, which means we can use I equals V over R to calculate current out of the battery, which is 4 amps, and we can use P equals I times V to calculate the total power, which is 48 watts. So now we just need to figure out how to get another value in my other two columns. Well, since this is a series circuit and we're not allowed to gain or lose any electrons, if we know that 4 amps of current leave the battery, and we know that 4 amps of current have to be coming back in the battery, that tells me 4 amps of current also have to be pushed through resistor 1, and 4 amps of current the same 4 amps have to be pushed through resistor 2 before we get back to the battery. So that means that I can put 2 more values in my table. I can say that the current through R1 is 4 amps and the current through R2 is also. Now we've got 2 known values in those other 2 columns, so we can use Ohm's law again. You have to use it sort of in reverse, right? I equals V over R. We're plugging in 4 equals V over 1 to calculate that. So 4 times 1 is 4. And for R2, it's going to be 4 equals V over 2. So 4 times 2 gives me 8 volts in R2. And then we use our power equation, P equals I times V, to calculate out those last 2 power values. Now the table, we got there with math and a little bit of logic, but the values in the table should make sense if you think about each row individually. So the voltage row, you should notice a few things about those voltage values. Thing number 1 to notice, 4 plus 8 is 12. It's like magic, right? Conservation of energy says that we have to use up all of our energy at the individual resistors that we got at the battery, and our math backs that up. So 4 plus 8 is 12. That's going to be true in a series circuit. The other thing is we should be using a higher percentage of our voltage in the larger resistor. So in this case, we see that the resistance of R2 is twice as much as the resistance in R1, and so it makes sense that the electrons have to use twice as much energy to push through that resistor than they did the other one. So 8 is bigger than 4 because 2 is bigger than 1. The current row makes sense, we've already talked about this, but because there is only one path through this circuit, the same number of electrons have to go through each location at the circuit every second by conservation of mass, so the current is the same. The resistance values make sense because overall this is a high resistance circuit with a bunch of resistors back to back, therefore we should have a more total resistance than we do individual resistors. And the last thing is the power, and that's also going to be a conservation of energy situation. You'll notice that the total power, 48, is equal to the 16 at the first one plus the 32 at the second. So energy is conserved because the total power used up is the same as the power provided by the battery. We also know that in this case, we are providing a lot more power to the second light bulb, twice as bright, right? 32 watts is twice as much power as the first bulb. And the reason is because even though the same number of electrons are going through each one of those bulbs, each electron uses more energy as it passes through the second one. So R2 is brighter by a factor of 2 because each electron uses more energy as it passes through. Let's go through the same process again with a parallel circuit and see what the VIRP table here looks like. So I'm actually going to take the same 2 resistors, the 2 ohm and the 1 ohm resistor, but this time I'm going to connect them in parallel instead of in series. And I'm going to put the same 12 volt battery in there, which means my VIRP table starts out the exact same way. VIRP on the left, 1 resistor, 2 resistors, and total. And even the known values are going to look exactly the same. We've got our 2 ohm and our 1 ohm resistor and our 12 volt battery. But that's where the similarities end. From here on out, everything is different. So don't get in the habit of doing the same thing on every table. You got to really think about what makes sense for the circuit that you've got. So the first question I ask myself is, should the total resistance be 3 again? Well, this is like a school day that's actually giving you a choice of 2 tests to take. You have options here, right? You certainly wouldn't say this is harder than taking, they're equivalently as hard as taking both tests back to back, because you really only have to pick one or the other. Actually, so the resistance, it does not make sense in this case to just add up those 2 resistor values to get 3. I think that's the most common error people make with these, is assuming that the resistance just adds always, but it doesn't in a parallel circuit. In fact, the resistance we're going to find out later on is actually less than even 1. It's less than the smallest resistor. It's kind of like providing two different hallways to go through makes it easier for traffic to go through, even if one of those hallways is small. Overall, the hallways provide more space, just like the wires provide more room for the electrons to go through. So we can't just add up the resistance. Well, what can we do? Well, we can realize that the electrons got 12 volts of energy going through the battery, and they have a choice of which path to take, but they only do one or the other. So if you're an electron that chooses R1, you're going to put all 12 of your energies in that resistor. And if you're an electron that chooses R2, you're going to put all 12 of your energies in that resistor, because they're different electrons, because it's two different paths. So you can put in your voltage values for R1 and R2 in this case. From here, you can go ahead and calculate I and V in those columns using your Ohm's law and your power equation. And so we've got two columns completely filled out. The last thing we need to do is get a third value or a second value for that total column. We can actually get there a lot of different ways. I usually think about current myself, but there's other ways to get there, as you'll see in a minute. So I think about, if I know that 6 electrons every second are going through R1 and 12 electrons every second are going through R2, how many electrons had to leave the battery to make that happen? Well, obviously, think about that junction where they split. If I'm going to have 6 go one way and 12 go the other, then I had to have 18 coming into that junction, which means the battery has to be spitting out 18 every second if I'm going to make that work. So I plug in 18 amps for current, and now I've got two values, which means I can calculate the other two values using Ohm's law and the power equation. Okie doke, let's take a look and see whether the values we calculated make sense in terms of concepts. So the voltage looks a little different than the other table, but this makes sense too, because since electrons are only going through one resistor per cycle in this circuit, the electrons are allowed to use all of their energy at that resistor. They don't have to save it for another resistor because they only have to go through one. So they're all going to be the same. The current makes sense as well, because as we talked about earlier, the 18 amps starts out, it splits into two paths, 6 and 12, and then it's going to come back together again and go back in the battery at 18. The other thing to note is that we get more current through the smaller resistor value. If you've heard people choose the path of least resistance, this is similar, although it's not everybody chooses that path, just most of the people. So in this case, because there is a 1 ohm and a 2 ohm resistor, twice as many electrons are going to go through the 1 ohm resistor than the 2 ohm resistor, which is why the current is twice as high for the smaller resistor. The resistance value makes sense as well, even though we don't really have a way to calculate it directly without an equation that I'm not going to give you guys. But you see that the total resistance is in fact less than even the smallest resistor in the circuit. So when you have a parallel circuit, be on the lookout for total resistance being a very small value, because electrons have a choice of paths. And then the last thing is power, which actually does work pretty much the same as it did with a series circuit. You'll notice that the power adds up. 72 plus 144 gives you 216, and that's because of conservation of energy. So energy provided by the battery is all used up in the circuit. And you'll also notice that in this case, it's a different bulb that's brighter. It's R2. It's the smaller resistor that's brighter. And the reason is because even though each electron is using the same amount of energy, twice as many electrons are going through that bulb than the other one, and therefore it gets more power. One more quick slide to compare and contrast series and parallel circuits. In the series circuit, we found that the higher resistor bulb was brighter, because when current was the same for both, more voltage meant more power. In a parallel circuit, we find that the lower resistor bulb is brighter, because when voltage is constant, then more current means more power. In a series circuit, we find that it has more overall resistance than the parallel circuit, because you have to go through those resistors one at a time. And that translates into less overall current and quite a bit less overall power for that circuit. If you look at the overall total power values, we're not generating nearly as much light in the series circuit as we are in parallel. And of course, the flip side is parallel circuits, because there is a less overall resistance, there's a lot more overall current, and that translates to more overall power. In a series circuit, you should know that a single switch anywhere in that circuit is going to turn on or off all the bulbs, which may be a good thing, but usually is a bad thing, because you usually don't want a single switch in your house to turn on and off all of the things in the room, just one thing at a time. So usually that's not a good thing. Whereas in parallel circuits, you can put switches on each of those pathways that can control just the individual bulbs. So that's another fun thing about parallel that's important when you think about comparing and contrasting. Okay, we've reached the end of this video. There was a lot there, so please take a few minutes to think about how do we use these tools to organize data, and how do we use equations to predict and model the behavior of complicated circuits. Thanks for watching.